So we're going to be looking at solving differential equations. This is a nice bit of pure maths which has a lot of real-world applications, in physics, computer science, and so on. It might sound a bit odd to include this under the integration chapter if they're differential equations, but effectively the idea is if you've got an equation with many derivatives in it, you're going to be using integration to reverse those derivatives and get yourself a solution to the differential equation. The first thing I want to do is probably just cover some terminology, just to make it clear what it is we're talking about when we're talking about differential equations, and then after that we'll take a look at how we can go about solving them. Okay, so the first thing we just want to establish is, what exactly is a differential equation? So a differential equation is, in some sense, a generalization of a regular equation, in which you've additionally got the possibility of including the first derivative or the second derivative or the third or so on of any one of the variables that you're talking about in the equation. So let me just, I can just make up some examples, for example. So let's say dy over dx plus x equals 2. This is an example of a differential equation. Okay, or we could have the second derivative of y with respect to x minus 3 times the first derivative equals 5, for example, right? Or equals 5 plus x, right? Or anything really. So the point is, there's nothing special about anything I've written here that's different to normal equations, except for the fact that we've now got additional possible terms we're allowed to include. We can include dy over dx, and we can include the second derivative of y with respect to x. Yeah. So that's how they differ from ordinary equations, but they're still the same as non-differential equations in the sense that they have a solution, and the solution to a differential equation is essentially just going to be a function of whichever variables you're interested in. So for instance, the differential equations I have here are all relating y as a function of x, and then you're getting the derivative of y with respect to x and the second derivative of y with respect to x. So the solutions to these are going to be something of the form y equals a function of x. Okay, but just so you've got some sort of grounding, this is what differential equations look like. Okay, and then let's just add a little bit of terminology here. So the order of a differential equation, this just means the highest derivative appearing in the equation. So an analogy to this is with polynomials, we can say the order of a polynomial is the highest power. So for example, if I've got a quadratic, that's order 2 polynomial. If I've got a cubic, that's an order 3 polynomial. Similarly, we would say this differential equation here, this is first order differential equation, because the highest derivative you've got is this, which is a first derivative. Okay, and in some sense the x, that's almost like a 0th derivative, where you haven't taken the derivative at all. And here, in the second example that I've made up, you've got a second order derivative. So therefore, the whole equation, we would say, is second order. Okay, so just pick whatever is the highest number of differentiations that's occurring, and that's your order. So this 2 here directly corresponds to the fact that it's second order. Okay, that's what we mean by the order of a differential equation, and it's analogous to the order of a polynomial. Okay, and then the next word I'd like to talk about is a general solution. Okay, a general solution to a differential equation. And what this effectively means is an expression describing all possible solutions. Okay, so we'll get a little bit more specific with this when we see some examples. But the idea is that a differential equation has usually more than one solution. It has many different solutions. You know, kind of like how a quadratic has, you know, 2 solutions and a cubic has 3 solutions. With differential equations, for many of them you'll have infinite solutions. But even though you've got an infinite amount of solutions, that doesn't mean that anything's possible, right? It's one of those, you know, common errors of thinking to think if there's an infinite amount of possibilities, then everything's possible. It's not. You can have an infinite amount of solutions, but they will all potentially take a very similar form, right? And that's what we mean when we talk about a general solution. It means somehow describing every single possible solution of a differential equation by using an expression. So just one expression which describes all of them. Okay. And then another bit of terminology you may hear then is a particular solution. Okay. And then you probably can sort of see where this is going. That just means a specific solution. Okay, so with if I give you a general solution, you can then sort of pick from that one specific solution. Okay, and there are many particular solutions, right? And all together, all of the many particular solutions form a general solution. Okay, so that's what we mean when we say particular solution. And then one last bit of terminology is boundary condition. Okay, and a boundary condition is effectively a piece of information. Okay, it's a piece of information which, you know, it's a piece of numerical information which allows you to go from a general solution to a specific solution, which narrows down a general solution to a specific solution. Okay, so the idea is, again, if I give you a differential equation, you'll only ever be able to get a general solution. Then if I give you an extra bit of information, a boundary condition, in addition to the differential equation, you'll be able to narrow it down from a general solution to a particular solution. Okay, cool. So if I use those words now, you'll hopefully have some idea of what I'm referring to. And I'll just mention that even though I've told you, you know, what the word order means, we're actually not in this session going to be looking at second order differential equations. We're going to keep it simple. We're going to start off with these kinds of differential equations, first order. So you shouldn't be seeing anything involving second derivatives. We're just going to start with first derivatives for now. So just to clarify some of these terms, I'm just going to use them with reference to a very simple example, which I'll just make up now. So let's take a really simple looking differential equation. I'm going to say the derivative of y with respect to x plus 2x equals 0. So now I want you to think, okay, how could I find an expression y equals something which will make this equation work, which if I plug it into that equation, it will be correct, right? For example, let's just say I guessed, right? And even if you see the answer straight away, that's fine. But let's just say, you know, I just guessed, right? Let's say I said y equals 5x. Is that possible? Well, let's try it out. Dy over dx is 5. Therefore, dy over dx plus 2x equals 5 plus 2x. Okay, that's definitely wrong. It doesn't equal 0. So that's clearly not a solution. So this is what I'm talking about when I say a solution of the equation. It's just an expression which will make this equation work. Okay, so now let's come up with an actual strategy instead of guessing. Let's try doing this. I'm going to change this into dy over dx equals minus 2x, so I'm just rearranging the equation. And now, if I have dy over dx equals minus 2x, if I integrate both sides, okay, if I just integrate with respect to x both sides, I'll end up with y equals what? It's going to be minus x squared, but plus c, right? And now we can hopefully get a sense of what's going on here. This is now a general solution, right? So that general solution describes an infinite amount of possibilities, right? Because we've just shown that y equals minus x squared should work, y equals minus x squared plus 1, you know, y equals minus x squared plus, I don't know, 5, y equals minus x squared plus pi. I mean, this c can be absolutely anything we like, okay? So there's an infinite amount of possibilities. This list of 4 elements I've written is actually an infinitely long list, but they still all have this specific form, okay? So these things that I've given, you know, I've given 4 examples of particular solutions, okay? These are the particular solutions. And if we want to summarize them all, we can say this is the general solution. And let's then say I've got a boundary condition. Okay, so I'll make up a boundary condition. So just so we can see what that sort of looks like. So a boundary condition is just some additional bit of numerical information. It could be something like when x equals 1, y equals 3, for example. Okay, that could be a boundary condition, right? Or a boundary condition could be when x equals 1, dy over dx equals 3, right? It can be anything of this kind of nature where you're saying 2 things are simultaneously true. Okay, but let's go with the simpler one I've just come up with. X equals 1, y equals 3. So in that case, we would have, if we substitute that in, we'd have 3 equals minus 1 squared plus c, which implies that c must be equal to 4. Okay, so that implies that y equals minus x squared plus 4. Okay, so that's just its own little thing going on there. If you were given a boundary condition, we can then reduce the general solution to a particular solution, which is what we have here. Okay, this thing here is just another example of a particular solution. Okay, it's not one of the ones I listed, but it doesn't matter, does it? Because that's just it's still taking clearly this form. Okay, so that's all the terminology sort of being used on a very simple example. So now let's look at you know, some more advanced examples of this kind of thing. Okay, so here you've been given a more complicated looking differential equation. So let's just note a few things. So the differential equation, well, that's this. Okay, x equals 1 when y equals 4. This thing here is a boundary condition. And what we are being asked to find, we want to find a particular solution in the form y equals f of x. So this thing here, this is the thing we're trying to find. It's a particular solution. So we're going to start off by finding a general solution, and then we're going to plug in this boundary condition, and we'll end up with a particular solution. Okay, so how are we going to solve this? Well, one thing to note, which is quite common at this level, is you've got this differential equation and it's using a mixture of y's and x's. Okay, so you've got x's all on the numerator, y's on the, sorry, x's on the denominator, y's on the numerator. And And then you've got your dy over dx, which is in some sense a mixture of both y and x, isn't it? And what we're going to do is we're going to manipulate this equation in such a way that we have x's all on one side and y's on the other side of the equality sign. Okay. The way we're going to do that is it might not immediately be obvious why, but I'm going to divide both sides by the -3 y minus 2 expression. Okay, and that gives me this. So this is just me having rearranged the equation. Okay, it's the same differential equation, just in a slightly different form. And now we're going to do a little trick here, which we call separating the variables. I mean, we've kind of separated them already, but we're going to do a trick here with the dy over dx. What we can do is we can, and I'm not going to go into detail about how this works or the proof, but I'm just going to teach you the technique for now. This dy over dx, it looks a bit like a fraction. It's not really a fraction, but for a bit of abuse of notation, we can do a trick which has been proven to work, and it is mathematically true. And that trick is to do the following. It's to almost treat this dy over dx like a fraction and bring the dx, multiply both sides in some sense by dx, bring that over here, and just apply integral signs. Okay, I'll just remove that bit there. So that is a true statement which can be derived from what we had previously. Okay, and what you have now is effectively two integrals which you can integrate, because on the left hand side it's a function of y being differentiated with respect to y, and on the right hand side you've got a function of x being differentiated with respect to x, and that in theory should be possible as long as the integrals are integrals that we know how to integrate. Now the left hand side, I'm going to make it a little bit simpler by bringing the -3 over to the other side. Okay, what I'm effectively doing is multiplying both sides by -3, and that works through the integrals perfectly fine, because if you multiply the outside of an integral by a constant, the constant just goes inside. Okay, so I multiplied both sides by -3. Now this expression here, you should be able to convert that into the sum of two fractions via partial fractions. I'm not going to do it for you now, as in I'm not going to show you the working for it, because that's something you've hopefully had enough practice of. Okay, if you do want a bit more practice, you can pause the video before I continue. But what you should end up for that right hand side, so we're not integrating it yet, I'm just expressing it as partial fractions, that is the same thing as this. Okay, and the left hand side will just keep as it is. Okay, so by partial fractions we've rearranged the right hand side. Now we can do our integration. The derivative of this bottom is the same as the top, so that works out nicely. And then, in case you're wondering about what happens with plus c, okay, so when we integrate, you're supposed to add c, and I didn't add it here, and at least I haven't so far added it to the right hand side. So the trick here is to just add it to one of the sides. I tend to just do it on the right hand side, and that's fine. Then you've expressed it in the most general form, and the reason for that is, if you imagine, let's say I added a constant here when I integrated and came down, and also added a constant here as I come down, all I'd have is two constants, two different constants potentially, added to both sides. But I can combine those into just a single constant added to one side. So this expression we have here is completely fine to describe the most general possibilities the most general solutions of this equation above. So it works completely fine just adding a plus c to just one side there. What we then need to do is combine all of these logs, and we're going to do a trick here. So this plus c, I'm going to change that to ln of some other number, k, let's say. I've just chosen k because it's a different letter to c, it doesn't matter. I could have even just put ln c again, to be honest. The point is that this thing here is still just a constant, but I'm expressing it in the form of a logarithm with the express intent of then being able to combine it with these other terms more easily, which we can now do. So I'll have ln of x plus 2, and then we've got minus, so it's dividing by 2x plus 1, and then we've got a plus here, so we multiply by the k inside this ln, so I can put the k here. Okay, so far so good, hopefully. Be very wary of this trick, yeah, because if I just had plus c, then it'd be a lot harder to combine it with this. But with this nice little trick, I can bring the constant, this constant of integration inside here. And that constant of integration is where all the generality comes from when we talk about the general solution. Okay, so now we're at this stage. Let's do e to the power of both sides. If we do that, it's just going to get rid of both lns. So now the equation I had before implies that this is the case. So we're getting even more simple now. And then I'm just going to add 2 to both sides. And this is now my general solution, right? It's y as a function of x, and it's general because there's still a constant in there which can be whatever we want. So if I set this k to be 5 or 7 or 1,000,000 or minus 3.7, doesn't matter, this equation will correctly solve this differential equation, right? We've just proven that. What we now want to do is use these boundary conditions to tell us what this k should be, because we're going to bring this general solution to a particular solution. So let's plug that in. So when y is 4, x is 1, so I'm going to get 3 all over, well, 3 in this instance, plus 2. That implies that 4 equals k plus 2, and that implies that k must be equal to 2. Okay, so then if k is equal to 2, I should make a note of that up here. Let's remove that working. And we can then just say y equals 2 lots of x plus 2 all over 2x plus 1 plus 2. And then with just a little bit more work, what we can do is simplify this slightly further. So I'm going to multiply that out. Yeah. And I'm going to force the numerator to look similar to the denominator by separating out that 4. So hopefully we can agree that's still the same. And then if we just move this to the left a bit, we have that this is equal to 1 plus 3 all over 2x plus 1 plus 2, which is the same thing as 3 plus 3 over 2x plus 1. And that is the particular solution. That's our particular solution here, okay? Which is the only expression, the only possible expression for which this differential equation will work and for which this boundary condition is also true. And that's how we solve a differential equation. So then just to sort of give this process a name, I mentioned it earlier, it was called separation of variables. There is a sort of formal way of characterizing these kinds of problems. Probably not that helpful, but it's worth writing down anyway, just because you will find it in the textbook. And it's, if you happen to have a differential equation which is in this form, dy over dx equals a function of x times some other function with a different name g of y. To solve that, you're going to do the following. You're going to say this is the same as the integral of 1 over the function of y with respect to y, being equal to the integral of f of x with respect to x. And hopefully you can see how I can get from this to this by dividing both sides by g of y and then separating out this dy and dx in the way that we did in the previous example. So from this you can get this, and this is in some sense a very specific form, when you happen to have it in this form, dy over dx equals that. But this technique of separating the dy and the dx can be used for other instances, not necessarily when it's just exactly in this form. And that should become clear from the type of question you're given. Okay, but that is the sort of textbook definition of separation of variables. So let's just do one last example. It'll hopefully be simpler than the one we just did, and we're just going to look at finding a general solution. Okay, feel free to have a go of it by yourself, by the way, if you want to. Otherwise, I'll just quickly do it now. Okay, so we're finding a general solution, no boundary conditions given, and with a bit of sort of manipulation of the variables, dividing and multiplying in your mind, you should hopefully be able to get this. Have we done that correctly? Yeah. Okay, so from that, with practice, you'll be able to see how you can just immediately knock that out. And it's simply a case of saying, I'm going to move this dx to the right, I'm going to move this tan y, divide it over to the left, this 1 plus x squared, that moves and divides over to the right, and then I just apply integral signs to both sides because I've separated the dy and dx, and you end up with this. And then from there, you're just doing your usual sort of integration. The right hand side looks quite easy. The derivative of the denominator is 2x. So therefore, I'm going to get a half of ln of the mod of 1 plus x squared. I'm going to add the plus c to the right hand side already. And on the left hand side, this is the integral of cot y. And that should be a standard result, the integral of cot y. That's ln of sine y. Yeah, that's ln of sine y. So let's stick that in straight away. Yeah, so the integral of cot x is ln of sine x, or the integral of cot y is ln of sine y. Okay, and hopefully you can see how what we're going to do now is use our trick with the plus c. I'm going to change that plus c to a ln k again. Right, you're not always going to do that, but in the case where you're getting logarithms, you should do. And then this half, let's get rid of that and just square root the inside of the log by putting it to the power of a half. Okay, so now everything's purely in logarithms with no coefficients on the outside. And then here we're adding logarithms, so I can multiply this k times the square root of 1 plus x squared. Raise both sides to the power of e. I get this. And we're pretty much done. You might sometimes also then see it being written like this, taking the inverse sine or arc sine of both sides, and you get this. Okay, and that's our general solution. And then you can pick any value of k you want, and the differential equation will still work. Okay, so let's have a look at our first question to try. I think I've got about 4 to give you. In this case, you've got an exponential in there, but it's just a case of separating the x and y variables and then putting in your boundary condition. Give that a go, see how you get on with it. Pause the video now. And your answer should be this. And then let's take a look at the next one. Getting a bit more complicated. This is e to the power of x plus y in brackets. The x plus y is in brackets. And then that's all multiplied by dy over dx. So just to make that completely clear, this whole thing is multiplying the dy over dx. If you need a hint, I can give it to you, but if you don't want one, you can pause the video now. Okay, and then my hint is, again, you want to separate x's from y's. This 2x is already by itself. These you're going to separate by presumably dividing or multiplying. In fact, you probably want to factor out the x on the right-hand side. And here on the left, this e to the x plus y, remember that's the same thing as e to the x times e to the y. And then it's a product, and you can separate that product by dividing. So you want to get all your y's and x's to one side. Then use the usual procedure with the separation of the variables. Okay? Pause the video now if you still need to give that a go. Right, and then the answer is this. And it's a general solution. You've got your plus c there. Okay, and now have a go at this one. Pause the video now. Okay, and then your solution is here. And finally, if you've got the time for it, I know I've given you quite a few questions. If you've got the time for it, do have a go at this one. It's quite interesting because this is going to show you a really nice relationship between this very simple looking differential equation and the equation of a circle. So give that one a go. Okay, and then your answer is here. So effectively, this differential equation describes circles. The solution of this differential equation is circles, which is quite interesting.